Hello everyone, and thanks for watching Edupedia World videos. In the previous video, we started learning about the wave properties of light, namely interference, and in this video, we learn about another property which is solely exhibited by waves, and that is called diffraction. Now the proper definition of diffraction is that it is the bending of waves around a corner when obstructed. Right? So let's see what happens when we have a beam of light. Let's say this is the beam of light, and just going like this from a torch, parallel beam of light, and we have a slit here which allows only a small portion of the light to go through. Now let's say the cross section of the beam has a diameter of 2 centimeters and this slit has a width of, let's say, 1 centimeter. Right, this looks much bigger than twice this, so let's say this is 4 centimeters. So we have a cross section parallel beam of light which has a cross sectional diameter of 4 centimeters, and then it passes through a slit of width 1 centimeter. So what will happen when we observe this on a screen? The portion of light will go straight through, some of it will be obstructed by the openings and some of it will go through, right? And this should be horizontal lines, by the way, and the small amount of light that will go through will create a small spot here which will be a bright spot, and the cross section of this bright spot, or the width of this bright spot, will be 1 centimeters. So this is actually a demonstration. This can be easily verified experimentally. You can do it at home with a torch, and this is the demonstration of the particle properties of light, or of the geometrical optics properties of light, in which light just goes through straight rectilinear propagating from one point to another. Now in this case there is no diffraction or bending of wave observed, because this dimension 1 centimeter is much greater than the wavelength of light. Right, so the first thing you need to remember is that diffraction is only observed when the dimension of opening is approximately of the order of the wavelength of light. Right, so what is the order of the wavelength of light? It is of the order of 400 to 700 nanometers. So if the width of this slit was of the order of 400 to 700 nanometers, or of the order of 10 to the power minus 7 meters, in that case we would just not see a single bright fringe, we would actually see bands of bright and dark light. Right? In fact, we've actually seen a small example of this already when we did the Young's double slit experiment. We took light, a parallel beam of light, that passed through one small slit, and then it passed through 2 slits, and after passing through 2 slits we got a pattern on a screen, right? Something like this. This would be the central maxima, which will be the midpoint, right? The central maxima like this. Yeah. So actually what would have happened if the dimensions of the openings of the slits were much greater than the dimensions of light? In that case only a small portion of this beam would have gone through, and since that beam would have seen an opening, an obstruction, we would have not seen any light over here. How is it possible that a straight parallel beam of light, horizontal beam of light, goes through this slit, and then a certain portion of the light comes out through this slit? And after coming out through this slit, it doesn't go like this or just parallel, it goes in all directions. Right? So sometimes you see light bending around these corners and going in all directions. Sometimes you'll see just light going straight through. What is the difference? Light goes straight through and behaves like what is called a light ray. A light ray is a straight line which just reflects and refracts. Other than that, it doesn't bend around any corners. So it behaves like a light ray, it behaves like particles, it behaves from the point of view of geometrical optics if the dimension of this opening is much greater than the dimension of the wavelength. right? And that is why in normal everyday occurrence you don't really see interference and diffraction, because if you have an opening that would be easily seen to the visible eye, the opening would have a dimension of the order of 1 centimeter or 1 millimeter or 0.1 millimeter, but not of the order of 10 to the power minus 7 meters, which is what is needed for diffraction effects to occur. When we do the Young's double slit experiment, the dimension of these slits are indeed the small d was the difference, the width between the slits, the distance between the slits. The dimension of these slits is actually of the order of 10 to the power minus 7 meters. Otherwise, this would not happen. Otherwise, the light beam would be obstructed here. So let's go back to the basics and see diffraction from the perspective of Huygens principle. Huygens principle, remember, I'll repeat it once, states that any point on an arbitrary surface, when reached by a wavefront, becomes a secondary source of light emitting secondary waves, and the disturbance beyond the surface results from the superposition of the secondary waves. So let's say I have a single point source, and then I have an opening here, and then I have a screen here. So what I would expect to see if it were just purely geometrical optics is one ray of light would go here, one ray of light would go here, and there would be rays of light going in between if this is the source, and everything beyond this would be completely dark. That is what we would expect if light were behaving like a light ray. But since light is actually composed of waves, the moment it reaches here, what happens is some light will go like this, some light will go like this, some light, the straight ones will go like this, maybe here some light goes like this. You get the point, right? It does not always travel in a straight line if there is no obstruction. Sometimes it will bend around corners and reach a wider area. If this were purely geometrical optics, this would be the only region where we would see light, right? So how does this explain from the point of view of Huygens principle? This is the source, this is the slit, and this is the screen. So when light rays go like this, then we know that is equivalent to wave fronts going like this, right? For a point source, wave fronts would be spherical, right? So wave fronts would keep going like this, and at one point wave fronts would reach this particular surface, right? Now this particular region is the only region that is open, every other part is obstructed. So at every other part, waves would be reflected backwards, and this is the only region in which waves would be transmitted forwards. So what will happen? This particular length, this particular surface, when it gets touched by a wavefront, it starts emitting secondary wavelets itself. And how would those wavelets look? This point would create wavelets something like this. I'll make the dotted ones in the middle, which will show you destructive interference. Solid ones are constructive. This is for this point. This point would become a source as well. Any point in the middle would become a source as well, right? And as these sources keep on traveling, you see that it reaches, envelopes would become like this, and it would reach a much wider area, which would, in terms of the light rays, look like this. So light rays would actually be spreading out as if this particular surface, this particular width of the slit was itself a source. They'll not just go in straight lines which pass through S, they'll spread out because of these diffraction effects. So this is the perspective of Huygens principle from which we can explain diffraction as well. Now let's see some of the standard forms of diffraction. The first one is Fraunhofer diffraction. These are named after the scientists who discovered them. First we'll do Fraunhofer diffraction for a slit, a wide slit, then we'll do it for a circular pinhole. Now the one difference between interference and diffraction as it pertains to your course is that the mathematics involved in interference of light is quite simple, and we were able to do it top to bottom, right? We were able to see everything out properly mathematically. However, when you start talking about diffraction, except in some very simple cases, the mathematics tends to be quite complicated. And so in many of these cases, I'm going to give you the final formula which you need to know in order to solve problems, but the derivation of that formula is not really in your course, right? So the first one we'll start with is Fraunhofer diffraction from a single slit, right? So in this case, we'll have light coming from some source and it will pass through a slit. Now the dimensions of the slit need to be very small. They need to be comparable to the dimensions of the wavelength of light, otherwise we would not see any diffraction effects. But for the sake of clarity, I am drawing a very big slit and I am drawing quite an enlarged figure, because particularly for diffraction and interference you need to understand it properly through the figure, because that's quite important. So let's say light, there's some source, light enters. All we are concerned with is that t is equal to 0. The moment when our experiment starts, this particular surface, the surface that does not have anything blocking it, this particular region, that will start behaving like a plane wave source. Now this would be a point source which would radiate equally in all directions. A plane source does not radiate equally in all directions, it radiates more in the forward direction, but we'll see that later when we come to another chapter. Right now all we are concerned with is that wavefronts are being created in this region. We are not concerned about how the wavefronts reach these regions, that is how the original source was created. Right. So if wavefronts reach this region, then any point between these 2 points would be a secondary source of waves. Right. So let's say waves from the 2 ends, the top and bottom end, reach this particular point. Let's call this point P. Let's say this is the center. And let's say the center makes an angle of theta. Now again we'll be using the assumptions which we used in YDSE, namely that the distance between the slit is much larger than any of the dimensions. So we'll be assuming that this angle is very, very small. We'll draw a perpendicular just like we did for YDSE. Let's say this total slit has a width of B. Right, I was going to use D, but that we use for YDSE, so let's call it B. Right, so this point and this point will have approximately the same phase. Right, because this point and this point will approximately have the same distance from P. Right, so they will cover the same distance in this length and this length. So the let's call this something A, B, C. So AP is equal to AC approximately. Is equal to PC, sorry. Right. So, and just we'll draw this slit too properly. So the path difference between a wave created at A and a wave created at B by the time they reach P is BC. Right. What is BC? If this angle is theta, this is theta, we know BC is equal to B sine theta. Right. Now actually we can't just take this path difference to be equal to some particular value. It's more complicated than that, because in a double slit experiment we just had 2 slits, that is 2 sources, but in this case every single point in between A and B will be its own source and we have to take care of all of them. And this is why you see what I mean when I say that the mathematics gets more complicated. However, there might be a special case which would greatly simplify things. What if, let's say this is A, this is BC, this is D, and this is E. So let's focus on ADE and ABC for a second, right? I'll just draw an enlarged version here. Right, A, D, E, B, C. This total is B, this should be one straight line. This total is B, so this is B by 2 and this is B by 2. This is theta. Right, so we were talking about the path difference between the waves created at A and B, and that would be BC. What is the path difference by the time they reach P of the waves created at A and D? That would be DE, which would be B by 2 sine theta. B by 2 sine theta is the path difference between the waves created here and here. Right, this distance is the path difference between waves created at A and P, because AP is approximately equal to EP is approximately equal to CP, also approximately equal to EP. Right, now what if it were so that B by 2 sine theta happened to be equal to lambda by 2, or actually n plus half lambda by 2. We'll just take lambda by 2 for the smallest case, but any n plus half lambda by 2 you know would give destructive interference. So let's assume that B sine theta by 2 is equal to lambda by 2. In that case, the path difference between a wave created at A and a wave created at D would be lambda by 2. So A and D would destructively interfere by the time they reach P. However, this is not only true for A and D, this is true for a point just below A and a point equally below D. It is also equally true for D and B. It is also equally true for this point and this point. Every single point will be completely out of phase with a point that is B by 2 below that point. Right, A will be completely out of phase with D. D will be completely out of phase with B. This midpoint will be completely out of phase with this midpoint. Any particular point will be completely out of phase with a point that is B by 2 below it. Therefore, the complete first half between AD will be in destructive interference with the second half, and at this point you will get a completely dark fringe. So actually taking care of the waves created by every point between A and B is quite complicated, but if we are lucky enough to see that the path difference between A and D is such that it is destructive interference, then it automatically means that the path difference between any point between AD and a point B by 2 below that, which is between D and B, would also be destructive interference, and so we would see a completely dark fringe at B. So the formula in this case to have a dark fringe would be quite a simple one. B sine theta is equal to lambda. Right. Now we'll see cases in which it becomes slightly more complicated, but I'll not show you the derivation like I showed in this case. I'll just give you directly the formulas, and I'll try to explain the formulas a little bit too. So the formula in this case we would want is E as a function of theta and I as a function of theta. E would mean the electric field at a point as a function of theta, and I would mean the intensity at the point as a function of theta, which would be proportional to the electric field square. So the general formula which we've seen by experimental basis, and we've derived it, though we won't do it here in this particular course, is that E is equal to E naught sine beta by beta, which means that I is equal to I naught, the intensity, sine square beta by beta square. Now what is beta? We wanted E as a function of theta, not E as a function of beta. So beta is actually equal to pi b by lambda sine theta. So beta is a function of theta itself, and E and I are both function of beta. So we are able to see how E and I behave as a function of theta. The graph, if you were to plot this, would be, I'll draw the graph for I, because I would always be positive, and the graph of I would be something like this. This is the sort of graph we've seen again and again. We saw this when we were talking about interference as well. And it just keeps going down. Right, this would be the central point where it would have its maximum value, which would be I naught. Now as theta approaches, this is sine theta by the way. So as theta approaches 0, sine theta approaches 0, so beta approaches 0. However, sine beta by beta, as beta approaches 0, actually approaches 1. It will not have a value exactly at 0, but any point near 0, it will approach the value 1. Therefore, when sine theta approaches 0, that is near the central maxima, the intensity will be a maximum I naught. Then the other intensities, if you were to calculate this, come out to be approximately, this is I naught by 22, and this next one is approximately I naught by 65. You don't need to remember it, I'm just giving you a rough idea of the scale. Right. Now, these two are important points. These two are the first dark fringes. This is the central bright fringe. And these two are dark fringes. Okay. Now, what does the dark fringe mean? It means the intensity and the electric field are 0. Intensity 0 means sine beta is equal to 0. What does sine beta equal to 0 mean? It either means theta is equal to 0, which we've already seen for I naught, or it means that sine beta is equal to sine of pi, which will be 0. That means this whole thing is pi, which means, or minus pi, which means sine theta is equal to plus minus lambda by b. So we see that there are 2 points. There are other points obviously for which this could be 2 pi, 3 pi, 4 pi, which will give us the remaining points. But if sine theta is equal to plus minus lambda by b, then beta is equal to plus minus pi, and the intensity is 0. So this is lambda by b, and this is minus lambda by b. These are the values of sine theta where you would not see any light at all. You would see a completely dark fringe. And by the way, sine theta is equal to plus minus lambda by b. This is called the angular divergence of diffracted ray. I'm going to rub this off completely now. Let's go back and look at what we've learned. We've seen a little bit of mathematics, though you might be somewhat confused because we haven't derived it. I've just given you the formulas. So let's go back to the basics and see what we've actually learned. We've learned that we could have any source of light, a point source, a beam, it doesn't matter, if that light passes through a small slit. Now a slit has to be very, very small compared to the wavelength of light. If the slit is not small, and let's say we have light coming like this, then we would just see a single bright spot here, right? You take light going like a beam, let's say from a torch, you pass it through a pinhole and it will just form a shadow here. You won't see any interference bands or waves. That would be true if this width is much larger than the wavelength of light, which it is in most practical cases. However, in a laboratory, you could have this width which would be much closer to the wavelength of the light. In that case, you would see diffraction effects. And instead of light going in a single straight line and creating just a single hole here, a single bright spot here, what it would do is it would create bands like this. This would be the central bright spot, right? Now we saw just before, and this intensity, if it is I0, this is I0 by 22. So this is less than 1/20th of the actual intensity, and we won't really be able to see this with the naked eye. The points where we'll see the zero intensities are points such that from here, this is the center, this is theta, this is theta. Sine theta, that would be minus theta actually. Sine theta is equal to plus minus lambda by b. That is the angular divergence, right? So this theta is lambda by b. We know b is the width of the slit, lambda is the wavelength of light, and that is the point where you would see the first dark fringe, right? Now if this distance were d, then you would actually able to calculate this as well. That would be theta multiplied by d, right? But right now we don't need to worry about that. Now also you need to see, as b gets larger, sine theta gets smaller, so theta gets smaller. So if this slit is very small, in that case you might see a pattern like this. If this slit is very large, then all you'll see is a pattern like this, which to us would look like just a single bright spot. So it's more of a matter of scale. If the width of the slit is very large, there will be diffraction always, but the diffraction would be something like this. These should be progressively increasing and decreasing, but you get the point. And as the width keeps decreasing, the diffraction starts becoming more and more like this. The wavelength starts spreading out more and more. The light starts spreading out more and more, and the divergence, angular divergence, will be plus minus lambda by b. Now this was the first case where we did it from a single slit. Now we'll do it from a circular hole. So up till now what happened was, we shined light through a single wide slit. When we were talking about a slit like this, now I'll try to draw the figure, though I don't know if I'll be able to properly. This is what it basically would look like. Light would go, and it is going through a slit which basically has the height, what we were calling the width from that side, but it has a big length, right? So if we had a screen and the screen was like this, right? Earlier we were looking at a screen like this from the right, and we were seeing bands like this, right? Those bands would actually look like this. This would be a completely dark band, bright band, dark band, bright band, dark band, bright band, right? So we would not see points, we would see bands, because there is a lot of width to the slit. It becomes completely different, however, if instead of having a wide slit with a small width, we actually start having a pinhole in which both the dimensions are very small. So in this case, now it's difficult to draw it properly. Now I'll just label it as a pinhole. But the difference is simply this. If right now we are looking perpendicular to the screen, however, if we were looking from here like this, in that case, in the first case, the slit would have looked to us to be something like this, now the pinhole will look to us to be something like this. So instead of light passing through a slit where this was B, now light will be passing through a pinhole, right? When light passes through a pinhole, what we get is, instead of wide bands which we were calling fringes, we actually get circles. We get bright spot, then we get a dark circle, then a bright circle, then a dark circle, right? And if we were to look at this with our eyes at this point, then instead of looking like bright and dark bands, what it would look to us would be a bright spot and then some dark region, and then some bright region, and then some dark region, and then some bright region, and then some dark region. So instead of seeing wide bands, what you would be seeing would be circular rings. So this geometry is very important to know the clear difference between a slit and a pinhole. Every time we've done slits, including a Young's double slit experiment, we've actually taken a slit like this, in which we allow a small light to pass through width p, but the length is quite a lot, and that's why we see bands like this. But however, right now we'll be seeing circular rings, right? So again, I'm just going to give you the formula right now. The first dark ring, now again, every time we talk about angular divergence, we'll be talking about something like this. This will be theta, right? So the first dark ring occurs at sine theta. Now plus minus is not needed because we are actually talking in a single direction. It's not just up and down, it's all around, right? Is equal to 1.22 lambda by b. Earlier we had lambda by b, now it becomes more complicated because of the circular geometry and everything else, ends up resulting in a factor of 1.22. So sine theta is equal to 1.22 lambda by b. What is b? Earlier it was this width of the slit, now it's the diameter of the pinhole. And obviously if this total distance is d, then the radius of the first dark ring, its sine theta will be 1.22 lambda by b, and its radius will be 1.22 lambda by b times d. Right, that's something which we saw in one of the very first videos of 11th class, that this radius multiplied by this distance is this angle, right? So that's something which we've used again and again. Okay, and this radius of the first dark ring is also called the radius of the diffraction disk. So 1.22 lambda by b would be the radius of the diffraction disk. Keep in mind, b is not the radius of the pinhole, it is the diameter of the pinhole. Okay. Now again, this tells us something quite phenomenal. It tells us that whenever light passes through a circular boundary, it will not create a bright spot, it will actually create bright and dark rings. Again, if the circular spot has a diameter which is much greater than the wavelength of light, then you would only see one single bright spot and the diffraction effects would be negligible. However, if the diameter of the pinhole is comparable to the wavelength of light, then you would easily be able to, just with the naked eye, see appreciable diffraction effects, right? And just what this broadly means is, light going in any direction let's say passes through a surface having a pinhole, this is all material, and it passes through the pinhole, and we look at it at the screen. I'm not very good with drawing as if it looks like it's three-dimensional, so forgive me for that. If light goes here, then we would see a single bright spot if this width was much greater than the wavelength. But if it was comparable to the wavelength, we would see a small bright spot, then a dark ring, then a bright ring, then a dark ring, then a bright ring, then a dark ring. Right. Now this happens no matter how you send the light through. If light goes through a pinhole, then it will have diffraction. Now one of the major problems this causes is in photography. Whenever you are taking an image, light is passing through a lens. Now a lens from the side looks like this, but if you look at it with your eyes at this point instead of towards the monitor, in that case the lens has a circular boundary. Right, and what we try to do is we try to increase this aperture or this diameter as much as possible, because if this diameter is large, then we would see a single bright spot instead of diffraction rings. When we are taking a photograph, we do not want to see diffraction rings, we want to see a clear image, and that's why the lenses tend to have a larger aperture whenever they are used for photography. This also means is that whenever you take the image of a point object from a lens, we've not studied geometrical optics now, we will study it after light waves in the next video, but by and large you know a little bit about geometrical optics. So it says that if you have a point here, a single point object, then you will never be able to have a point image of that point object. If you have a screen here, in that case it will always be a small bright spot followed by a dark ring, then a bright ring, then a dark ring. You will never have a point image of a point object, right? For that you would need to have an infinite aperture. What can happen is the radius of this first diffraction disk would be 1.22 lambda d by b, right? Where b is this aperture. We can see that the more we increase the aperture, the smaller the radius of diffraction, which is good. D is this total distance, and lambda is the wavelength of light, right? And this is again, like I said, very important in photography when you are forming images of objects which pass through a lens. What this basically tells us is that a single point object after passing through a lens will not have a single point image, it will have an image something like this. And this creates a problem when you are trying to resolve two different images, because if you want two different images, one image of an object is like this, the other image is like this, then it's fine. But if the first image is like this, the second image is like this, then those images will be overlapping and you will not be able to resolve them properly. So a scientist by the surname of Rayleigh created a criteria by which he decided when images were just resolved. Images could be either well resolved, not resolved at all, or just resolved. Just resolved images, the definition was that if the center of one bright disk falls on the edge of the other, right? So let's just talk about the bright disks. If there are 2 point objects, one of them has a bright disk like this, the other one of them has a bright disk like this. They just overlap and you can see a difference between them. So these images would be called resolved. However, if the first bright disk is like this and the second bright disk is like this, then they overlap a lot and you won't be able to resolve between them, right? This can be shown much clearly in an intensity map. Intensity here would look something like this. There would be a dip in intensity in the middle and intensity would be large outside. Here the intensity would look like this. Intensity would be maximum in the middle, right? Now as you take these two centers, I'll just draw them like this now. Right, the total disk is the bright disk which has a certain radius of the bright diffraction disk, right? Now if what happens is this center falls on the edge of this one and this center falls on the edge of this one, that is the exact point when you start seeing a dip. If it is like this, this is the center of the second one. In that case, that is just the point where we start seeing a small dip between the two. We are just able to differentiate between the two images instead of looking at them as the same image. So that is called Rayleigh criterion for resolving images. They say that two images are just resolved if the center of the bright disk of one falls on the edge of the bright disk of the other. If they are closer than that, we would not see any dip in the intensity, we would see it like this. If they are farther apart than that, then we would see something like this, where still we would see overlapping. If they are not overlapping, that means the distance between the center is more than the combined radius. We don't want that. We just want to be able to see some dip in between. In that case, the distance between the centers is just equal to the radius of either of the diffraction disks. So this completes diffraction. In the next video, we'll see a phenomena which not only is it just specific to light waves like interference and diffraction, but it is only specific to transverse light waves. It does not occur for longitudinal ones. Light waves are all transverse. It occurs only for transverse waves, not longitudinal ones. That's why we didn't see it in sound, and that is something you've seen a little bit before. It's called polarization. Right? Polarization only for transverse waves, never for longitudinal waves. That's what we'll do in the next video. Thank you.